Okay, so we will talk about more on key exchange protocol, like typically 3-party key exchange protocol. So far we have seen if there are 2-party, how we can do the key exchange. So we have the Diffie-Hellman key exchange protocol for 2-party, we have seen that. So Alice and Bob. So now we talk about 3-party. If we have 3 parties, then key exchange protocol. Okay, so how 3-party can, so if you have 2-party like Alice and Bob, now we know that they can just by Diffie-Hellman, because in a single round they can do the key exchange, like Alice can choose. So they have a group G, so this is typically ZP star, it could be other group also. So where P is a prime, then and G is a generator of this group, small g. So Alice compute G to the power A, Bob is choosing this B, so Bob compute G to the power B. So then Alice is Bob is computing G to the power A to the power B mod P, so which is basically G to the power AB mod P, which is the key, and Bob is receiving this G to the power B, and Bob is having G to the power A, so Bob is computing G to the power A, so G to the power AB mod P. So this is basically same key. So they agree with the common key in a single round. So this is single round protocol. So single round key exchange protocol. So just one communication is required to establish this key. Now they can use this secret key. This is the symmetric key. So then now they can use this symmetric key for their further communication, encryption, decryption. Okay. Now this is 2 round. Now we want to extend this, or we want to say this, how we can do the key exchange if there are 3-party. So we have, if we have 3-party, say Alice, Bob, and we have another party, say Rob. Okay. Now the question is how they can agree with a common key. So key exchange between 3-party. So we want to see whether we can extend the Diffie-Hellman protocol for this 3-party key exchange protocol. So if they are choosing this ABC, so Bob is choosing, so they are under Z, so G be a group ZP star say. It could be general group also, but for simplicity we are taking ZP star, and ZP star is a group under multiplication where P is a prime. So ZP star is basically ZP minus 0. We have to remove the additive identity element, then this will form a cyclic group. And so if it is cyclic group, means it has a generator, and suppose G is a generator of this group. Okay. So now how they can agree with a common key? So basically we need to do like this. So this cannot be done one single round, because if Alice is sending G to the power A, so say Rob, if Rob is sending G to the power C, Alice is sending G to the power A, and Bob is sending G to the power B, then how they can agree? I mean, so they can mutually agree with a common key, like these 2-party can agree with a K1, which is basically, but we want they should agree with a single key. So like under this, so what Rob can do, so Rob can agree with a G to the power A, G to the power AC with, so basically there will be 2 keys, like G to the power AC will be agreed with Alice. For each party there will be 2 keys. So, say for Alice will receiving G to the power C. So, Alice will compute G to the power C to the power A. So, this is G to the power AC, obviously mod P, and Alice is receiving G to the power B from Bob. So, G to the power B to the power A. So, G to the power AB. So, basically this is K1, this is K2. So, each party is receiving pair of key to communicate with the other party. So, but that we do not want, we want this 3 party should agree with a single key, symmetric key K. So, how we can achieve that? So, that we have to talk about, but that is not possible in a 1 round. So, this is a 2 round protocol. So, let us we are using Diffie-Hellman. So, choosing B. So, they are this is sending G to the power A and sending G to the power B. So, they are computing G to the power AB. So, this is the key they are computing. So, this is Rob is having G to the power C. Now, they are agreed with a common key G to the power AB mod P. So, now this is with both the party G to the power AB, this is the K. I mean G to the power AB is now with both the party. Now, what they can do? They can apply a hash function on it, and this is basically Y. So, Y is we want a hash function such that it is taking this group element G from to the order of the group. So, 0 1. So, we want to have a index on this, so that we can use again for G to the power Y and send it to over the public channel. So, we want a hash function to be G2. So, maybe 0 1 2 up to order of the group. I mean here we are dealing with P. So, it is basically P minus 1. Okay. It is basically P minus 1, or in general it is order of the group. So, if we apply this hash function on this, it is a hash function is digest function. So, if we apply the hash function on this, so it will give us Y. So, Y is now, so if Y is now P minus 1. So, now we can use Y as a index. So, now this Y is shared between these 2 parties. Y is known to these 2 parties. Now, we can compute G to the power Y and send it to over the public channel, and then Rob can compute G to the power C. Okay. So, now, so G to the power C is receiving by Alice Bob. So, they can compute the G to the power. So, Alice can compute G to the power C. G to the power C is getting from Rob over public channel. So, Alice can compute G to the power C to the power Y, which is Bob also can compute, and so this is basically G to the power C Y mod P, and Rob is getting G to the power Y and Rob is having C. So, Rob can compute G to the power Y to the power C. So, see, this is basically G to the power C Y mod P. So, this is the common key shared between these 2 parties. So, this is basically G to the power C Y mod P. So, this is the key, this is K. So, this K is shared between these 3 parties. So, now this K. So, K is basically G to the power C Y mod P. So, this is the 3 party. So, C Y. This is the 3 party key exchange protocol. We are using the underlying Diffie-Hellman, but this is 2 round. First round these 2 they agree with a common key, then second round we need. So, this is a 2 round protocol, 2 round, not a single round. Now, we want to talk about how we can have a single round protocol. Okay. So, this thing, this is basically this also can be attacked by the active adversary. For to prevent that, again we have to talk about the authentication. We can send this by signing the message like this. So, anyway, I am not going to do that now, because we are just talking about key exchange protocol. So, in this lecture we are not considering the attacks. Okay. So, this is the 2 round. Now, we have to talk about how we can make it single round. So, for this what we do, we want to define a function which is called bilinear pairing, and then you will use this function on a protocol which is called Jokes protocol to have a single round key exchange. Okay. So, let us talk about bilinear pairing. Bilinear pairing. How we can define a bilinear pairing? Okay, it is a pairing, basically bilinear pairing. Okay. So, for that let us have a group, say G1, let G1 be a additive group. Okay. And it is a cyclic group also, but it is the operation is additive sense. So, that means our operation is like, if we take 2 element from, so G1 say, so it is cyclic group. So, let P be a primitive element, P is a primitive element, of this group. Okay. Then the elements are basically P, 2P, because it is in additive sense, 3P like this, 4P like this. So, in general say AP, so where A is lies between, so it is between 1 less than A less than equal to order of this group. A is the index, but it is in additive sense, it is not power. So, the operation is additive sense. So, it is just AP to P like this. Okay. So, then yeah. So, basically if you take 2 elements P Q, I mean here P is a primitive element. So, if you take R S, then the operation is R plus S, additive sense, it is in G1, and typically this group is a elliptic curve groups. This is coming from elliptic curve points. So, we know how to have the elliptic curve points over ZP. Now, this group need to be a elliptic curve group in order to have the anyway we may talk about the example of pairing. So, this is a group G1. Now, we have another group G2 which is in multiplicative sense. We have another group G2, let G2 be a group, cyclic group, be a multiplicative group. Multiplicative group means operation is in multiplicative sense. So, nothing but this. So, G1 is basically plus sense, is a group, and this is also a group. So, we have 2 groups G1 and G2. Okay. So, now we defined a function E which is from G1 cross G1 to G2. E is a function from G1 cross G1 to G2. So, this is G1. Okay. So, now we call this function to be a bilinear function or bilinear mapping, a bilinear pairing. This function is called pairing if it has these following properties. If we take EAP BQ for any two element PQ from G1, this should give us E PQ to the power AB, and this is for all PQ from G1 and AB are any two index AB. So, maybe 0 less than AB less than order of the group. Okay. If this is true for all such AB. So, this is so so PQ are the element from G1. So, AP means P plus P plus P A times, BQ means Q plus Q plus Q B times. So, these are two elements in G1. So, this is a function from G1 cross G2 to G2. So, then the result will be an, so then this will be an element in G2 and this should be written as, this is in multiplicative sense. So, it should be written as EPQ to the power AB. Okay. So, this is one property and second property is degenerate property. So, that means if P is a generator of this group, P is a primitive element or generator of G1, then EPP must be a generator of G2. So, that means EPP should not be 1, then EPP is not equal to 1. What is 1? 1 is the identity element of G2. This one is the identity element of G2. Okay. So, that means if it is not the identity element, then it must generate this group. Basically, this is a primitive element of G2. This is a generator or the primitive element of G2, or P is a primitive element of G1. Okay. So, this condition must be there. This is called degeneracy condition. So, that means if you take a primitive element or the generator of this group, then EPP. So, P is generating this group G1. So, EPP must generate the group G2. So, that means EPP should not be 1, or 1 is the, because this is multiplicative sense G2. So, 1 is the identity element. So, this is third property is that there should be an efficient algorithm to compute this pairing. We should have a efficient algorithm to compute EPQ for ERS, because P we have used for the generator belongs to G1. So, we must have a efficient algorithm. Efficient means there should have a polynomial time algorithm, efficient in the sense polynomial time. So, we should have a polynomial time algorithm for compute this pairing. So, if these three, so E is called pairing, E is called bilinear pairing or just a pairing. Pairing is usually defined on, it is called pairing. This function E is called pairing. So, there should have a algorithm, polynomial time algorithm to compute this pairing. So, okay, so this is the definition of pairing. So, if a function E is having these three properties, then it is called a pairing on bilinear pairing. Now, how to construct such a function? That part is not so easy. So, example of a pairing, it is not so easy. So, there are two examples of pairing in the literature like Tate pairing and Weyl pairing, but they are all coming from. So, for pairing are coming from G1. This G1 is a elliptic curve group. For pairing, G1 is elliptic curve points, say over ZP, or so. Then one can define the Tate pairing or Weyl pairing. Okay, so but the G1 should be that is why elliptic curve point we know in additive sense. So, it may not be over ZP, it is maybe over some other group. So, but over ZP we can have this pairing, but this needs lots of abstract algebra concept like divisibility theorem, divisibility condition, how we can define the this. So, this part we are not going to the details of this in this class, particularly for this course. This is out of the scope of this course, but there is a huge literature on this construction of such pairing. Okay, but pairing exists. Okay, now question is how we can use this for having a three-party key exchange protocol in a single round. So, that is called Jokes protocol. Jokes key exchange scheme. So, Jokes use this pairing for doing this key exchange. Okay, so there are three parties: Alice, Bob, and Rolf. Will you mind if I take Oscar? I treat Oscar is always a bad person, but anyway, maybe I can take Oscar. Now he became friends of Alice and Bob, which contradict the literature. Oscar is always chosen as a bad guy, but anyway, this is they are agreeing with the common key. So, here we are trusting Oscar. So, Oscar is now became friend of Alice and Bob. Okay, so now they want to agree with a common key k in a single round. So, how they can do it? So, they want to make use of this what is called pairing. Okay, so what they do? So, they know this G1. So, G1 is known to all, G1, G2, anyway G1 is known to all, and suppose P is a generator of G1, let P be there. So, first of all they have to choose a group G1 on which this pairing is defined, and this and suppose order of this group is say P minus 1 or P, and then G is a generator, P is a generator of this group, let P be a, and this is usually the elliptic curve group. So, this is usually additive group. So, we have a this operation is additive sense, let P be the primitive element of this group. Okay. So, now all this party they choose a cigarette. So, now they have this G1 is public now, and this P is also public. Now, they all choose a cigarette A, B, C. Okay. So, where A, B, C are both coming from. So, A, B, C are both coming from G1 minus 1. Okay. So, now Alice will do what? So, these are typical cigarette to each of this party respectively. So, A is cigarette to Alice, which is we can say cigarette, B is cigarette to Bob, C is cigarette to Oscar. So, A is sending to AP Bob is sending to BP and Oscar is sending to CP over this public channel. So, that means they are all getting this value. Okay. So, Alice, Bob and Oscar, this is over broadcasting. So, they are broadcasting. So, they are all getting these values. Alice is getting BP, CP, Bob is already having BP. So, Bob is getting APCP like this. Okay. So, now how they can agree with the common key? So, what Alice is doing? So, Alice is getting this value BP and CP. So, what Alice will do? Alice will compute the pairing EBP CP. So, if Alice will compute EBP CP, then it will be basically, this is pairing. So, it is basically EPP to the power BC. Now, Alice will compute this to the power A, because A is known to Alice. So, this is this to the power A. So, this is basically EPP to the power ABC. So, this is Alice is doing. Alice is having A. Now, Alice is getting BP CP over this public channel from other two party. Then Alice can compute the pairing function on this 2 point BP CP, and Alice can do the powering up to the power A, because A is known to Alice. So, then this is basically by properties of bilinear pairing. So, this is basically EPP to the power BC and we have to the power A. So, EPP to the power ABC. So, this is now EPP to the power ABC is now known to Alice. Now, what Bob can do? So, Bob is having B. So, Bob is getting APCP from other two party. So, Bob will compute EAP CP to the power B. So, this is basically EPP to the power APP to the power AC to the power B. So, this is basically EPP to the power ABC. Okay. Because Bob is getting APBCP. So, Bob will just compute this function. So, that is why this function should be computationally efficient, otherwise there is no question of computing this. So, now Bob is also agreeing with EPP to the power ABC. Now, what Oscar will do? So, Oscar is receiving APBP from Alice and Bob. So, Oscar will compute EAP BP to the power C. Oscar is having the secret C. So, this is basically EPP to the power AB to the power C. So, this is basically EPP to the power ABC. So, now Oscar is also having this APP to the power ABC. So, this is the secret key shared between these three parties. So, this is the key. So, this is our key. So, if k is equal to this, if this is k, then this k is agreed between these three parties. So, this is just a one round communication. So, they are just communicating one round. So, Alice is sending AP, Bob is sending BP, Oscar is sending CP, and then they are by computing this, they are agreed with the common key k. And now, once they have the key k, now they can securely communicate over the public channel using symmetric key encryption. So, this is the two party key exchange, but if you have three party, multi party, then in current literature there are some attempt for constructing the multi party pairing instead of bilinear pairing, multilinear pairing. Okay. So, those can be used to but those are under current theme of the research. Thank you.